Hello everyone and welcome back to lecture 6. So in this part we are going to look at what is the critical thickness of insulation, okay, and what is the importance of this critical thickness of insulation. So let's say that you have a cylindrical system again, and it's a pipe. So it's a 3D system with the height, with the length of the pipe as h, okay. So what if you add a layer of insulation to this pipe? So what is going to happen? Okay. So let's say you have a pipe of radius R1, and the radius of the pipe plus the insulation is R2. It means that R2 gives you the thickness of this insulation. And the resistance due to insulation is R insulation. And outside this pipe, you are having again a convective heat transfer due to the environment. The heat is being lost to the environment, and that is R convection. Okay. Just like we did in part 1, let's look at the heat resistance due to conduction. It should be equal to R resistance of insulation, and as we develop in part 1, that's the same equation. And then we have the heat resistance due to convection, and again similar to the first part, we have R convection is equal to 1 over HP 2 pi R2H. Okay, we have the two resistances that are involved in the heat transfer. Now, if you look at, for example, the total resistance of this system, so the total resistance, let's say R T, should be equal to the sum of these two resistances. Okay, the resistance due to insulation plus the resistance due to convection outside the pipe. Now, if you look at that, if you increase the thickness of insulation, and our general understanding is that if you want to reduce the heat loss, just increase the resistance, the thickness of the insulation. It means that by making the insulation thicker, um, the resistance should increase and heat loss should reduce. Okay, so that is our general understanding when we are talking about, for example, a simple system like a wall or something, or a window. Okay, but for cylindrical systems, it is actually kind of a paradox, in the sense that when you are increasing R2, it means that you are increasing the thickness of the insulation. So by increasing R2, you are actually increasing the resistance due to insulation, okay, or the resistance due to conduction. But on the other hand, if you look that when you're increasing R2 here, you are actually um, decreasing the R convection. Okay, so it means that the total resistance is actually based on the value of R2, and it's kind of a resultant of these two competing phenomena. Okay, so one is increasing the resistance while the other one is decreasing the resistance. Okay, so it means that there will be a value of R2 where this RT will be minimum, and as such we have the maximum heat loss to the environment. Okay, so that is exactly what is explained here, what I just explained. If you look at now the value of R2, so the value of R2 at which the heat loss is maximum, it means the heat resistance to the system is minimum, and that radius is what we call the critical radius of insulation. And in a simple way, it gives us the thickness of insulation that we can use. Okay, so let's say you have again a system of the pipe that we previously seen, and here we are looking at the resistance, that is the total resistance, sum of these two individual resistances. So if you put the value of what we calculated in the previous slide in this equation here, and if you take now the denominator as common and do some simple algebraic simplification, we get this equation here. Okay, and we know that the heat transfer rate clearly varies when we are increasing the thickness of the insulation. Okay, it means that we are increasing R2. So the value of R2, where we will have the maximum heat transfer, so it means that we can take a differential of this equation that we developed on previous slide and make it equal to 0. So that will give us the maximum heat transfer. Okay, so the point at which the value of R2 where the heat transfer is maximum. So that is the differential equation for that. And from mathematics, we know that if we have, let's say, two variables are multiplying and the sum that the multiplication is equal to 0, it means that either one of the two variables should be 0. Okay, but if you look at this part of the equation, we can see that this part cannot be 0 because lambda insulation is positive, h is positive, so these cannot be 0. So all these parameters are positive, they are not equal to 0, so it can't be 0, but this part can be equal to 0 because if this part is 0, multiplying with a positive value will give 0. Okay, so we have this equation now, and if you now take this term, for example, on this side and do some further simplification, so we can cut the value of R2 because it's appearing here as a square, so that we can cancel out the square, and then we have just one R2, and we can write the value of R2 is equal to lambda of insulation divided by HB. Okay, so if you look at this equation, the reason why the value of R convection is decreasing when you are increasing R2 is because we are increasing. So for example, we can write it also this equation as HB is equal to lambda of insulation divided by R2. Okay, so you can see here that when R2 is increasing, actually HB, that is the heat transfer coefficient, that is decreasing. Okay, and the reason this heat transfer coefficient is decreasing because when R2 is increasing, we are actually giving it the surface area is increasing. Okay, so by increasing the surface area, the heat transfer loss to the system is increasing as well. Okay, so we can write this R2. So here, obviously, in this system, R2 was a parameter that was given, but we can generalize this equation as for a cylindrical system, RC is equal to lambda of insulation divided by H node. So lambda of insulation is the thermal conductivity of insulation, and H node will be the outside heat transfer coefficient. Okay, and once you control RC, you can control H node. Okay, so what it means that when you are, for example, if the radius of insulation of a pipe is equal to the critical radius, okay, the heat loss will be maximized. Okay, and it means that when you are, for example, this is a pipe and you want to insulate it, you need to know what is the value of RC, because if, for example, you are below RC, so if you are below RC, adding more insulation actually increases the heat loss. Okay, so it means that if you are below the value of RC, and you are making the insulation thicker, instead of saving energy, you are making the system lose more energy. Okay, and that is one of the reason small pipes, we leave them uninsulated than insulating them and increase the heat loss. While when you are above the value of RC, let's say you are at such a thickness that your total R2 or R is above RC, it means that adding more insulation reduce the heat loss. Okay, so it means that when you make when your value of R is above RC, making the insulation thicker actually save you energy because it reduces the heat loss. This value of RC is very important in the design of insulation system. Okay, and this formulation that we developed is based on geometry. Okay, so this expression can only be used for the case of cylindrical systems. Okay, now if you change your geometry, for example, if you are looking at a spherical system or if you're looking at a sphere, and you are, let's say, some reaction is happening inside this sphere and you want to insulate this system. Okay, so you have to calculate the value of RC, and if you use the same logic that we, for example, developed for cylindrical system, if you use the same process, the RC value would be equal to 2 lambda over H naught. Okay, So this 2 comes from the geometry. So it means that the value of RC very much depend on the geometry itself. Okay. For a linear system where you have, let's say, for a window, when you have just like a rectangular system. So in this case, you don't have the value of RC, because by increasing the thickness, when you are increasing the thickness, you are just making the system, for example, increases resistance, and by that you are saving the heat loss. Okay, but compared to the rectangular system, cylindrical system, and spherical system, when you increase the value of insulation or the thickness of insulation, you have to be careful that what is its relation compared to RC. Okay. Now, if your sphere is hollow, the total thermal resistance of that hollow sphere is given by this expression. Okay, so this is, I'm just showing you for the purpose of just for you to know, but you don't have to memorize it. You don't have to drive it, because this is out of the scope of your course. But it is just to show you that for different geometries, you have different values of RC. Okay. So that is all for this part. Thank you for your time.